excited?
Oh yeah.
Oh yeah, can't wait. All right. Guess all the stragglers that are going to straggle in have straggled. Okay, well, I will begin. So, welcome everyone to mmWave Basics and a few test challenges we'll sprinkle in throughout the way. My name is Randy Becker. I am our 5G Testbed Program Director at Keysight Technologies. I'm from Santa Rosa, California, which is the Keysight headquarters. And if you don't know where that is, that's about an hour north of San Francisco, in the middle of the wine country there. That's where we do the majority of our RF and microwave development on signal generators, spectrum analyzers, and network analyzers. So, if you thought this was the advanced class, this is not the advanced class. Some of you look like you may be looking for the advanced material. This is definitely the basics area. Next year we'll cover the advanced material and show how to derive the integral form of Maxwell's equations and get to the differential form, which is quite exciting. But today we'll keep the math mostly out of, or all of it really. A few housekeeping notes are in order. So, first of all, you might be thinking to yourself, he looks fairly calm, collected, suave, debonair. And you know what the reason is? It's because of these, isn't it? You also can get a pair of these if you visit the Keysight booth, so that's a little commercial. Also, I have prepared 4,962 slides for you this afternoon. I spent all last week doing that, and I feel mostly compelled to go over each one of them in great detail, which should be exciting. Karen's going to lock the door so you can't escape. So we should be out of here by 10 p.m. or so.
Can those slides be downloaded, or are they already in the material?
They should already be in the IMS cyberspace. They pinged me and I put them there, so I don't know where that location is.
Okay.
So that was the bad news. The good news is I spent all of last night throwing away and rejecting all of the slides that were not the best, and we're left now with just the finest slides. So hopefully we should be out of here by 5 o'clock so we can go back to the exhibitor area. There's a happy hour at 5, so nobody wants to miss that. Okay, so here's the, and something else exciting. There's 2 more exciting things. I have 2 guest speakers coming. So I have Mr. Malcolm Robinson, also from Keysight. He's going to do a little section on over-the-air, which should be quite exciting. And then I have a Mr. Greg Jew, who will be in here a little bit later to do a live demo to sort of illustrate some of the concepts we'll talk about. So those will be 2 little additions. Okay, so here's a quick agenda. So we'll do an introduction to sort of set the stage for what we're going to talk about. Why are we here? Why do people care about these things? Then we'll talk about connectors and waveguides. This is an area that seems to get, that needs some attention, not too much attention. I get excited about this and often take too long to go through this section. The over-the-air measurements, which I mentioned, and then we'll spend a bit of time talking about system optimization and architecture. Things that we need to think about to get the best performance out of these setups, particularly at the higher frequencies and wider bandwidths. And then, of course, we'll have some time for questions. And if you do have a question, you can just let me know, and we can answer a question on the fly if we need to. And if anybody wants to come up to the front, there's lots of empty seats up here. Typically, I find the most learning occurs in the areas up front, but I can see nobody's going to move, so that's okay too. All right, does that sound good? Yes?
Yeah.
All right, well, we begin. So, why do we care about all of this stuff? What's going on in the industry? So, in the 5G area, we have basically, everybody I think knows this, all of the service providers want to be the first to market with 5G capability, and that comes in two forms. So we have access, getting the bandwidth to the end users, and also we have to get that information from the base stations back to the core network over the backhaul. So there's kind of two fronts on applications for 5G, or wider bandwidth in 5G, I should say. But there's also other areas, but largely a lot of the comms focus is around this 5G at the moment. So there's a variety of work occurring now. So there is still 5G, doesn't mean necessarily all millimeter wave and wide bandwidth. There is definitely work happening at sub 6 gigahertz, but there's heavy interest at the 28 and 39 gigahertz. And then there's a lot of additional focus at the higher frequencies in the millimeter wave region as well. As probably many of you know, Verizon has already published a specification for their sort of pre-5G, which is based on an LTE-like signal. That there's a whole ecosystem around that, people trying to gear up for supporting that. And then we have the official 3GPP new radio, what they're calling in our new radio, what the term of the new radio for 5G will be. We're expecting the first release of the specification to be available at the end of this year in December. So we'll be seeing increased activity with that. And of course, you as the R&D engineers have these new devices that you want to test, and there's a lot of maybe uncertainty in what's going on, and you want the best performance possible out of the test setups. So we'll cover today how to extract the last dB of performance out of these systems. I had one engineer tell me one time, he said, I want to make the instrument cry, and then I want to back it off 1 dB. Tell me how to do that. So we're going to show you a few of those things this afternoon. Okay, so why are we talking about wider bandwidths? And well, those are basically, that's how one of the main reasons, or one of the main ways we're going to get higher throughput to the users. Everybody wants more things on demand all the time, so that's no surprise. But at the wider bandwidths, this causes a number of challenges like phase noise, frequency response, and at wider bandwidths, this means more noise, and we'll look at that in a little bit. Some other things where the wider bandwidths are available, of course, are largely at the higher frequencies, so microwave and millimeter wave. And as we go to the higher frequencies, what happens? The wavelengths become smaller. So a little thought exercise. Everybody knows what 60 hertz is, right? Yes? Does that mean anything to anyone? 60 hertz? Yes? This should be the power line frequency for the AC mains in the United States, and other parts of the world is 50 hertz, so similar. But let's think for a moment, what is the wavelength of a 60 hertz signal? Who can quickly tell me what that is? Something large. In fact, it's
Many kilometers.
5,000 kilometers, actually. Whoa. So, so that's for the people that are from not the US. If you're in the US, we would use the imperial system, and that would be about 3,100 miles. So it's the width of the mainland United States, right? One wave, one period of 60 hertz, it would cross the entire United States. Now you could imagine a little thought experiment. If you shifted that waveform by the width of California and then added it back to that original waveform, it would still more or less look like a sine wave, right? So you can see where I'm going with this. As the wavelength becomes smaller, for the same amount of shift, it can have a big impact on the overall signal, right? So you get to a place where those would totally cancel out. So as we go to the higher frequencies, the physical tolerances on the components themselves, the whole layout, the geometry becomes much more critical. So you can kind of see here from DC to daylight, it's starting here kind of at 1 gigahertz, which is already a pretty high frequency in itself. At if you took 100 megahertz. The wavelength there is about 3 meters, so you know, something a little taller than I am. At 30 gigahertz, where we're talking about all of this new activity for 5G, at 30 gigahertz, the wavelength would be about 1 centimeter, right? So about like this. And then if we get to millimeter waves, we talk about 100 gigahertz, then the wavelength is about 3 centimeters, right? So it's really tiny. So you can imagine, yes, in fact, the wavelengths are on the order of the size of the physical components themselves. So we'll talk about this as we go through the presentation. So a few comments about the regulatory landscape. So the FCC has introduced some new spectrum in the US in the millimeter wave area, extending that this unlicensed area from 57 all the way to 71 gigahertz, which opens up new spectrum for people to use, which can be pretty interesting, a lot of bandwidth there. There's also other regions of the world are exploring other areas. So another comment about the spectrum is that it's relatively new to the commercial space, like for communications, but it's been used for a long time in other industries, right? So for like radar and backhaul are using microwave and millimeter wave. But what's new is mobility, right? How do most of these were fixed kinds of communications, but now we're going to have to do beam steering and tracking to account for the higher losses at these higher frequencies. So this is sort of a new thing, a new complexity being added to everything else that we're doing. Okay, so a quick chart here that shows the different commercial applications. So we have wireless LAN, LTE, the bandwidths they use for single carrier. Some of these technologies use something called carrier aggregation or channel bonding to increase the bandwidth. So this just gives us a little idea of the bandwidths and their use of them with carrier aggregation and some of the mobility requirements. Okay, so now the question is, do higher frequencies always give us wider bandwidth? Interesting. Well, let's explore this. So the first thing we need to consider is what happens to the signal-to-noise ratio for a system if we keep the power constant. So if we go back to the days when wideband CDMA was considered wide. Does anybody know how wide wideband CDMA was?
3.84 megahertz.
3.84 megahertz was exactly the chip rate. It had a bandwidth, a channel spacing of 5 megahertz. So now we're talking about bandwidths that can be a gigahertz or multiple gigahertz. So if we thought about the power, so we had our wideband CDMA signal here, and we have quite a bit of range between the top of that signal and the noise floor. Now if we take that same amount of power and we spread it out over 2 gigahertz or more bandwidth, the power spectral density has to decrease. And so now your range from the top of that signal to the noise floor is much smaller. Well, that's going to impact your EVM potentially, your ability to maintain a proper link. So that's what this line illustrates here. So you can see this is just sort of an arbitrary simulation that we did just to illustrate the concept. So as we go wider in bandwidth, the signal-to-noise ratio linearly decreases. Okay, so that makes sense. So now we'll overlay on top of this the channel capacity. So the two variables that we can change here are the bandwidth and the signal-to-noise ratio. And as we go from relatively narrow bandwidths up to extremely wide bandwidths, we see that the channel capacity is initially increasing quite rapidly. So we add more bandwidth, we get more capacity. But as we get over here where we're adding additional bandwidth, the signal-to-noise ratio is becoming lower, and so our ability to maintain, to get additional capacity is diminished. So there's diminishing returns for adding more bandwidth. And then we can also plot on top of that the spectral efficiency. So the efficiency of how well we're using the spectrum is also important, particularly at sub-6 gigahertz, where the spectrum is very expensive and very limited. So here we're plotting several different types of technologies and their relative spectral efficiencies. So we have high-performance backhaul over here with very high modulation orders. Then we have a wireless LAN and LTE with more modest modulation orders, a little lower power or efficiency, and then things like 802.11ad using wider bandwidths and not quite as efficient as some of the other ones. So this is just gives you some starting point for thinking about, okay, is wider bandwidths always the answer? And it can be an answer, but it also, you have to think about the other elements that are in play there. Okay, so a few general observations about millimeter waves. First, they don't bend around corners. They're also easily blocked by things that are not blocked at RF, right? So they might have trouble going through different types of medium like walls. They do bounce around a lot. A significant reflector in a room can be relatively small. They act more like light. As we mentioned, the physical tolerances have to be much tighter due to the smaller wavelengths. And generating power at these higher frequencies is also problematic, right? So getting good efficiency and getting enough power to make something work is a challenge. And the components themselves, even things like the cables and adapters, are very lossy and extremely expensive at these higher frequencies. Okay, so this brings me to the next part. So thinking about cables and connectors, what is important there? What do we need to think about? So here is an example of what we call a flexible 5G testbed. And the reason I'm showing this here is kind of a couple of reasons. One, to do this work at the higher frequencies and these very wide bandwidths, you get into some of these more custom configurations. There's not a single instrument that you can purchase off the shelf to do all of this work. It's often a collection of different instruments to be able to get to the bandwidth and the frequency at these higher bandwidth frequencies. And so you can see there would be a number of different cables and adapters and connections that you need to make to put all of this together. And so ensuring that you have a good quality cables is important, and I will give you some examples of this. So this is one example of a high performance flexible test bed that Keysight has put together. We have various variations of that, and just to give you a simple example of what we could do, you might say, well, what is sort of the cutting edge in the terms of bandwidth and frequencies that we could generate and analyze of some device under test? So I have exactly this on the next slide. So you might look at this and say, well, that doesn't look interesting, but let me point out a couple of the important characteristics that should make you say, whoa. All right. So what we're looking at here is a signal we generated with one of our arbitrary waveform generators that we upconverted to millimeter wave at 83.5 gigahertz. And I put this green marker here, this has a width of 10 gigahertz. So you can see we're generating a signal that's 10 gigahertz wide. We used an external mixer to upconvert that signal. And you know the mixer has sum and difference. So we're seeing the sum and the difference products at the output of the mixer. And we can actually demodulate that, and that's shown on the link at the bottom. So I won't bore you with those details. That's a YouTube video that shows how we did that. Okay, so Now, the next question. How many of you here have something that looks like this in your lab or one of your coworkers? Yes? This is terrible. So the question here is, what's wrong with this picture?
It's a mess.
It's a complete mess. This is everything. This is like a complete no-no. Everything you could do here is wrong. So we have here, there's a power splitter. There's some adapters, a screw to something. This wrench, that's terrible. Should be a torque wrench. We have a filter, another adapter, a mixer, the memory stick that I've been looking for the last 2 months, and a paper clip. None of these things belongs in that box, and they don't need to be stored that way. The reason I mention this is because you may know, you may not know, a lot of those little tiny parts, very expensive, and they're very fragile. So that little thing there, that 50 gigahertz power splitter is about $2,200. So you don't want to treat it that way. Some of these other more common 2.4 millimeter adapters, those are about $800. Even some of these waveguide to coax transitions, the 1 millimeter ones, those are about $3,000. So you just don't want to throw them into the drawer and think they're going to work well the next time you want to use them. Okay, so here's something I see all the time. People putting a connector like this on the table. That's a no-no. You should store it like this, right with the end caps on there, and it goes back in its protective sleeve when you're done. This is the proper way, but I see this all the time. What's wrong with that, you might ask? Well, the center pin can become damaged. You can get dirt in there, and once a connector's been damaged, and you try and mate it with another cable or adapter, it can damage those. And so now you have like this virus that is spread around your whole lab, and now everything needs to be replaced. And especially, you can imagine you had one of those brand new 110 gigahertz spectrum analyzers with that very fragile 1 millimeter connector, and then you just damaged it. And then you had to go to your boss and say, I need to send that back and have that replaced and recalibrated. That's not going to be an exciting day or an exciting conversation you want to have. So, a few other things about connectors. So connectors come in a variety of different classes, as we know: metrology grade, instrument grade, field grade. And I'm showing here just a quick illustration of some SMA connectors, and you can tell the SMA connector because of the dielectric in the middle. The more high precision connectors always use an air dielectric, and they're more expensive because the tolerances are tighter and they're harder to assemble. But you can tell quickly by looking at a connector if it's a precision connector if it has the air dielectric. Okay, so a couple of do's and don'ts. I think this should be self-explanatory. I won't go into too much detail here, but you want to keep connectors clean. You want to use the plastic end caps when you store them. You never want to touch the ends of the cable connectors or adapters. That's bad. You don't want to get oils on there and potentially bend that center conductor, and never store them as I showed. I would never do that, although I do see some of my colleagues do this, and it makes me cringe. So a technique that I've learned over the years to sort of stop this is when you get a new cable or adapter, you want to keep that in your control at all times, and then you want to lock it up in a drawer, and then when somebody asks to borrow it, you say, I don't know. Do you have a 2.4 to 1.85 adapter? I don't know. I don't see any around here. And that's what will keep somebody from destroying your expensive adapters. Okay, it's important to visually inspect all of them before use. A lot of people don't do this, but if there's a piece of dirt or something in there, that can cause immediate damage if you try and connect it to another adapter or cable. And you want to make sure you use the proper technique when connecting these. And I see this also a lot with some of the newer, let's say, interns that we have from time to time. They want to turn the entire, they want to rotate the adapter into a net, let's say. So a lot of the instruments have male connectors, and they want to take an adapter and screw it right into the instrument, which is a no-no because that center conductor is turning inside we call that, just lost my train of thought here. The center conductor turning inside the collet, there we go. And that would cause damage. Okay, so a little quick quiz. Who knows what the proper torque setting is for one of these common 3.5 millimeter connectors?
0.7 Newton meters?
It's 0.9, right?
We have 0.7, 0.9 Newton meters. Anyone else? Okay, here we go. How about this? So here's a list of possibilities, both in the metric system and the imperial system. Does that help? It's one of those.
It's 0.9.
Hmm?
I stick with it. I think it's 0.9.
0.9. The 0.9 is correct. So this is the right answer. So 0.9 Newton meters or 8 inch-pounds is the right torque wrench you want to use. Now the next question is, why do we use a torque wrench? Two important reasons.
Repeatability.
Don't over-torque.
Repeatability, yes. We want to make repeatable connections every time we make a measurement, right? So we don't want the result of our measurement to change every time we connect the cable or adapter. So we want to have it make a repeatable contact and connection every time. And then the other reason is we don't want to over-tighten it and cause damage. So over-tightening is another common thing if you don't use a torque wrench and you just use a wrench. And it's easy to apply too much torque, especially on the 1 millimeter connectors, which have a much lower torque setting. And easy to snap those off, and then that's another sad day, of course. Okay, now here's an interesting chart that I threw together that covers all of the common connectors that we would use in the RF, millimeter wave, microwave area. So you see on the left here a number of the different connector types. So we have the BNC type N SMA all the way to 1 millimeter connectors. And you also see here the rated frequency and the maximum usable frequency. So you might ask yourself, why are there two different frequencies? What does that mean? And the answer is the adapters and cables are rated to conduct only one mode. We want to use them in a single propagation mode. If we go and try and use the cable at higher frequencies, additional modes can propagate that have different velocities. And so what you'll have at the output are multiple signals arriving at different times, and we have dispersion. So that's one of the reasons for the rated frequency. And of course, the attenuation will also be higher as you go higher in frequency too. So these two are different in that as we start to get close to the higher frequencies, there can be some resonances, particularly caused by some of those dielectric beads that hold the center conductor in place in those precision connectors. Those will cause little resonances, and those can be calibrated out of the system usually and don't cause too much trouble. But if we go to higher frequencies, if we go above this max usable, then you'll get into that area where propagation modes, other propagation modes will occur, and that's not good. You'll also see over here, another thing to be aware of is the N connector, which is good up to about 18 gigahertz. You can go up to 26 gigahertz with some designs. These are available in both 50 and 75 ohms. And the center conductor is larger on one of those. And if you try and mate it with the other one, that will cause permanent damage. Irreversible permanent damage. I guess that's what permanent means. You'll also see here, these two, when you connect them, the design of that connector, the center conductor engages first. And the reason that's a thing to be aware of is that you can imagine when you're mating these connectors together, you could be coming in at an angle, and that would cause damage unless you're aligned directly straight on. So that occurs for both the SMA and 3.5. These other connector types were designed that the center pin engages last and largely prevents that type of damage. Also to note, these three here that are shaded in dark green, these are compatible, so they have the same threads, and you can safely make them together. And these two with the lighter green, these are compatible, so the 2.4 and the 1.85. And just as a little history, you can see where the connector type came from. And HP actually, which is now Keysight, invented a lot of these, or had their hand in developing those connector types, which is a little interesting fact. Okay, so what are factors that determine connector quality? So I gave some of those just like prices of what you would pay for some of those adapters and connectors. And it is possible you could go find less expensive adapters and connectors. So what's the difference in the two types that you might find? Because you can find an array of different qualities. So what are the factors that determine the connector quality? So first, it's the precision with which the components are manufactured. So not all are manufactured in the same way, even though it looks like it might be hard to tell from the eye. There is quite a bit of work that goes into that. Also, the materials that are used to make the connector are important, especially the choice of the material and what type of plating may or may not be used on some of the internal parts, and the overall design of the component. So you might think an adapter is an adapter. I have a connector that's one size on one end and goes to a different size on the other end, so all is well. What could be so hard with that? But actually, the design of the connector is very important in getting good performance. So as an example, here's a little diagram I put together that shows, here's the center pin, here's the diameter of the inner conductor on the one end, and it's stepping up to a larger size to be compatible with the other connector type that you have on the other end. So there's a discontinuity here inside that adapter. But you also have to change the size of the outer conductor as well. And if you weren't thinking about that, you might say, well, I'll make this step change on the inner conductor and the outer conductor occur at the same place in the adapter. And that would yield something that works, but actually if you offset these from each other, it improves the SWR. And so those are some of the things that go into making a good adapter, and not necessarily something that all manufacturers would do. So there's a lot of science and art behind this, which seems like, oh, it's just a little adapter. I found one at Radio Shack for $5, so I'll use that one, but not necessarily the best choice. Okay, so here's a quick look at the connectors themselves. So here's the SMA, you can see with the dielectric, and